that gets us, from what I can tell, I think we're done. That gets us this whole thing. That is our program. Now, what do we want our program to do? We can tell our program to do things here in the Arduino, of course, by saying include mini tank. Of course, we need to create one from the blueprint. So we take mini tank, blueprint, mini tank. There we go. And then of course, did we finish we didn't do a begin routine. We're missing something. We're missing our almighty begin to initialize everything. And of course, our mini tank needs to have a begin routine to initialize everything and fan out all these initializations like we talked about before. Okay, and then begin routine. I like to put that right underneath the blueprint usually. Right underneath the creation. There we go. The begin routine will take all of our objects and apply the begin routines of all of our objects, which is going to be our eyes and our tracks. So, our tracks dot begin, and of course our eyes dot begin. So there we go. Almost forgot one of the most important things. There we go. So now we say mini tank dot begin. Makes sense to me. So when this Arduino boots up and runs this setup program, it's only going to run this once. So as soon as you apply power, it's going to run this setup program, whatever's in here in this context. It runs whatever code's in here, and then that's it. It only runs it once. And as soon as it gets done with that, it runs this program loop, and it loops over and over and over and over, and over until you pull the power away. So in our program loop, we want to say mini tank dot go forward, in the same tradition as this other thing. And then if mini tank is stopped, of course, if it is stopped, if it's not moving forward, even after we told it to go forward, mini tank dot select new direction. That's it. It's done. That's the same program as this guy. Okay, it's the same. It should work pretty much exactly the same. A little bit of timing. I changed a delay on these a little bit because it was, the original was going a little too far. It should work. It should function. Let's find out. Let's build it. And we didn't even have any errors. That's cool. I expected about a dozen errors actually. And I'm going to plug this into this and flash it. What do you think? I'll flash this thing. There we go. It is doing that other thing where I was testing the servo or the stepper. Okay, it flashed it. Cool. And let's go save this and let me go play with it and see what happens. Okay, after some bit of testing with this thing, the only mistake I see in it so far is back over here at our eyes, like I suspected. It actually, the far right is negative 90, far left is 90. The far maximum right would be negative 90, and maximum left would be 90. So, as I suspected, it was the other way around. In other words, I thought that this was 0 and this was 180, but actually this is 0 and this is 180. So, that's the only correction so far. Let's save that, flash it again, test it again. It's a good thing I wrote that bounds checking the way I did, see? And I kind of suspected that. That's why I went ahead and did that. Okay, so after a little bit more testing, I did find another gotcha. And that's here in the mini tank CPP file. The jump back seems to be a bit much, so I'm going to reduce that to 140. And another gotcha. Ross, get your head out of your patootie. Is checking the encroaching distance. If it's less than the encroaching distance, it's stopping. Well, if it's actually, if it's less than 25, well, if it's actually 10 or less, it's still going to be less than 25, and it's going to stop. So it's never going to actually go to the pathway blocked. So what I need to do is I need to check to see if something's blocking it first, which is the lowest value, the shortest thing, and then if it's not blocking, then check for encroaching. Sort of got it backwards. And what's happening is it's not jumping back when it's really close. It's just simply stopping no matter what. So a little gotcha in there. We will correct this. Like I say, I made most of this program straight off the hip, just straight out of my head. So, I don't expect it to be perfect the first time around. But we're pretty close. Pretty close. So this should fix that. That's the only problem I've seen so far playing with this thing for, I played with it a good half an hour or so. Checked all the different scenarios. Alright. Let's flash it in and go again and check it again. And here we go. There. That should flash it, and we should be good. Every other scenario seemed to come out okay. So I thought I would add this in. Mistakes. Nobody's perfect, but I think pointing out the mistakes as you go along is just as important a process as coding it the first time. And also, you should prove all your code. You should go through and check all your routines and actually make sure they function before you release something into the world and say, yeah, it's 100% perfect. I don't ever consider my code 100% perfect, but I do consider my code very solid. So, yeah, that's where we're at. Okay, now that we've played with this thing, let's see if we can make some improvements. One area that I'd like to further improve from what I've already got would be the sonic sensor, because it's always a sore point with these little robots and things that use these sensors. So how could we improve on what we have already? We've already done some improvements over what most people do with these sensors. Let's see if we can make a further improvement. Why don't we put a range instead of saying, hey, it has to match exactly? We could speed this thing up and make it give us feedback with less number of retries. If we say, how about if the last measured, if what I last measured and what I'm measuring now are within like a certain width or range. Let's say if it's 12 to 15, it's, we'll call it good. Or if it's 8 to 17, maybe it's not so good. We can also do averaging, and I've done averaging with the sonic sensor. I started out trying to do averaging with the sonic sensor, and I actually ended up with more noise that way. If you just simply take averaging, for some reason, it's not that good. But I think if we put a range of like, let's say if it's within like 3, within like 3 centimeters, or let me see if I got this little ruler here. Let's say if it's within. I stole my wife's sewing machine. Strip over here, she's sewing. From here to here from there to there is about 3 centimeters. So I think if we had a range of 3 centimeters, that would be acceptable to me. And the reason why I say this is because if that thing's in motion, it's going to measure, boom, 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 boom. If it's moving fast, it's going to measure. It's not going to measure consecutively one to the next all the time. It's always going to have a little bit of range, or it can have a little bit of range in between solid signals. So why don't we we could program that out of it, and we could say, hey, if it's within a certain range, then we're going to call that, we can call that good too. So let's do that. Let's improve this a little further. Let's take it another step. And of course, to get a range, you need a difference. And to do a difference, we need to do the same thing we did with our angular stepper motor routine. I think we had this difference routine right here. And I think we can do that again. Because we inlined this, I'm thinking we'll just inline it again. So there's no reason to make this common to multiple different subroutines. I think we'll just make the same inline diff function on the other subroutine. Yeah, or we could make a common. We could make a. Why don't we do that? Just for fun, just for tutorial's sake, we'll make a utility or a class that's common, or a set of functions that's common to our project. How about we do that? We'll call it, in fact, we won't even use a object. We'll just make a class, and we'll actually create it as a structure. Why don't we say, what would be common to the, we'll just call it functions. How about that? Functions. So this is, this is one way of sharing information. And do we want to call it mini tank functions or just functions? Nah, we'll call it functions. That sounds good to me. And we'll do it without a namespace this time. And instead of a class, we will say struct, or a structure, and then we will say functions template. We'll go old school, and then we can say, okay, now we can go to our difference function, let's say in our angular stepper motor, and why don't we make that common to multiple objects. In fact, why don't we do this? Why don't we one-up it? Well, we just call it functions. There we go. And we'll put it here, which makes it basically a static object. In other words, create a structure, which is basically a public class. Everything in it is public by default. And instead of naming it as an idea, we're going to say, hey, instead of an idea, I want you to actually create it. Actually create it on the fly. And that's how you would do that. You would just put the name at the very end. And then, of course, and of course, when we do that, we have to put our code or our idea, the idea of a function and how to do it all in the same place. So that's how this would work. And then we just say void. And then, of course, we need our data types include. We don't need all the Arduino library just to get our data types, but we can say standard integers header, so it knows what these data types are. There we go. And instead of calling this mdiff, why don't we say difference 8-bit. There we go. Yeah, it looks pretty good. Yeah. And instead of void, obviously, a dummy. We need to return the difference between the two, which would be unsigned integer 8-bit. There we go. There we go. Now what that does is that creates a public structure of functions, so we can get to it by saying functions dot whatever functions we put in there. And of course, let's shorten this up so it looks a little better. Else. This is more of an old school way of doing things. Just wanted to show this. Now, there's a warning that says, hey, this has never been used before. It's very common with C++ to say that about something that's common to an entire project or common library. So there's a way to get around that, or there's a way to stop this warning, and I'll show that too. But I want to show how to share something publicly, like just make something totally public, how I do it usually. I don't like to use define, and I don't like to use the precompiler. I like to use an actual structure or put it in a collection somewhere. Sometimes I'll make a namespace and make an object out of it. But in this case, we'll do it without an object. We'll just say functions. And of course, now that we have something called functions, we can then include this functions.h in our places like our Angular stepper motor. Let's say we had this inline function here that we created that was private to only this. If we go here and we delete this 8-bit difference, the ability to have an 8-bit differencing function, we still need to be able to get the difference right here in our set angle, like we did way back in our project. So how we would do that is we would simply include that here at the top of our CPP file. Say include, we wanted to share this, include functions. And then of course, now we have the ability to say functions dot difference 8-bit. There we go. That's how that would work. And of course, any place we include our functions header file now that we created, we can have access to this common collection of code space. So we can use it there, and then we can use it in our sonic sensor so that we don't have to write another one. We can simply say, hey, in our sonic sensor code space, now we can say while functions dot difference 8-bit between two things, our feedback comma last measured feedback, while functions, and of course let's split this into multiple lines so it's easier to read, and retries is greater than 0. There we go. While these things are happening, and we will put this in a set of parentheses. While the difference is greater than allowed error, and then we can make an enumeration out of allowed error. Max number of retries, allowed error. And actually it's a hysteresis, so we could use the name hysteresis if we want. And we will say 3 centimeters. How do we look up the word hysteresis? Okay, I had to go look up that word, how to spell it correctly. Make sure I didn't butcher it too badly. Hysteresis. Hysteresis means dead zone. We'll call it dead zone so that those not technically savvy. There we go. Those not so technically savvy can relate to that. I know I can relate to it. Greater than dead zone. So there we can use this 8-bit differentiating function to determine a dead zone. And the retries are greater than 0, which means we still have this countdown. That looks good. I like it. It's a little more cryptic though, and harder to understand. So can we rewrite this where it's easy to understand without increasing the amount of code that executes? Actually, we can. We can do it with if statements and break statements, believe it or not. So how we can do this is we can say while true, which means run this loop forever. And then we can say if retries is greater than 0, actually if retries equals 0, break. Dummy. There we go. And we can say if break. And we will essentially end up with the same thing. But it's a little easier to read. There we go. I think we just improved on that thing. We have a dead zone of 3 centimeters. We can actually comment that if we want to. Not a big fan of comments. And dead zone in CM. There we go. Yeah. I think that would improve it further. And of course, 10 centimeters. I thought 10 centimeters was awful close with the robot. Awfully close. That's only a distance of this far in front of the sensor. Let me go get the robot and put this in perspective. Of course, this should be less than. So it has to be within the dead zone before it's allowed to continue. What I thought about next is here in our mini tank under jump back, the mechanism that makes it jump back, or the logic, the original logic too. We went off completely off the original program for this thing and made it function as close to this, as close to the same as it did. But this jump back function, we decreased it slightly, but I think we decreased it a little much. So I think 180, 200. They had it originally was a little closer, but here where we do the jump back, right here, the pathway block distance up 10 centimeters here. I think we need to adjust this, and why don't we say centimeters, encroaching distance, centimeters. If we take 10 centimeters, that's only this far, which in respect to the robot, with respect to the robot, looking at it straight on, that's only, that's only like roughly right here, 10 centimeters, there we go. It's only roughly that far, which is, quite close. You have to be almost up against it. And I put this little bumper bar when I built it. I made this little bumper bar so that if it bumps up against something completely, it doesn't block its ability to turn. I think it's too close. I think it should be about, I don't know, 15 centimeters maybe. 15 centimeters is more like how far away it should be. Yeah, that's more like it. So why don't we adjust that to 15 centimeters? And then, why don't we make this 30? So we'll improve that too. There we go. That might improve it, make it a little better, so that it doesn't slam up against something before it decides it wants to stop, or if something gets in its block. Because at 10 centimeters, what happens is if I take something and suddenly, and suddenly throw it in front of the base of this thing, like 10 centimeters away, which is about this far. By the time the motor stops and backs up, it usually wants to try to bump it. So at 15 centimeters, it'll be less likely to do that. So that's why I wanted to increase that. So after playing with this thing for a while, you realize that there are some improvements that can be made. So that's what I want to do here. And that's the whole point of designing something. You can improve, you can tweak, and you'll notice it's really easy to go in here and find what you need to improve on it, versus some program that you wrote. You have to scratch your head against the wall about 15 hours to figure out, how do I get to that? So, yeah, I'm gonna go play with it again.